So let's talk about the method that we are going to use to define the seismic forces, which is the simple method for doing that, which is the equivalent lateral force method. In this, loosely speaking, on this method we distribute part of the seismic base shear to each one of the floors of our structure. Okay, so and as a result, static forces are going to be applied. First, they're going to be generated by robot and then applied to rigid or semi-rigid horizontal diaphragms or vertical elements. Okay, this is the simplest method to define seismic loads, but you should be aware the codes, Americans and Europeans ones, limit its application depending on the plan and height regularity of the structure. Okay, so if you have a very weird and complex structure, you may need to do a model and a spectral seismic calculation, model analysis and spectral seismic calculation. Okay, this is you may do this if you have a regular plan and a regular plan structure. Okay, with nothing crazy, which is the case of our structure. So the step number one is the definition of the stories that we already done. Okay. So step number two is the definition of seismic analysis load case. You simply open the analysis type dialog box, press the new button, then this window will appear and you select the seismic equivalent lateral force method. If you need to do a seismic analysis, you first need to do the model analysis, okay? As this is the simplest case, this is the equivalent lateral force method, you don't have to select the model analysis because the model or the frequencies of the several mode shapes of our structure may be calculated approximately depending on the regulation that you are using. Okay. Now in step number three, you jump to the definition of the seismic analysis parameters. Okay. As you may see, this is a dialog box that you are going to see, and you may select a precise model analysis case or user defined or also approximate depending on the seismic code. And if you select the precise model analysis to find the mode shapes and the fundamental period of your structure, you may define the model analysis parameters in this box. Okay. So to finish that, you need to define the mass that is going to be used in the seismic conditions of a structure. So you do that on the load to mass conversion, also in the analysis types. The best way to do it is to add mass. Okay, you simply convert the cases that you think that you need to convert. Normally dead loads, and 30%, at least in Europe, is like that. 30% or 20% of the live load, okay? And you define that here, and the robot is going to convert that load case to mass and use it in the model analysis to define and to find the fundamental periods of your structure. Okay, you should add the mass to dynamic mass, includes converted masses in all dynamic cases. Okay, so I convert the dead load 1, dead load 2, and 20% of the live load, and the robot is going to use all this mass in all the dynamic cases. Okay, and you should use that in order to avoid overlapping representation of load and mass on the structure. This is a recommendation by Arthur Kozakowski and Rafa Gavenda, who did the webinar on seismic analysis, which is really good, and you may find the link over here. You should take a look at that link. So now let's do it. Let's configure basic seismic load. Okay, we will use the equivalent lateral load seismic load from the analysis types menu. Okay, so I'm going to press this button over here. And now I'm pressing new. I'm going to select seismic equivalent lateral force method. Okay. We are going to use the American Society of Civil Engineers 710. Okay, very good. The direction of eccentricities. For the load definition, we will select all of them, just like they did in this exercise, and we are going to use on the method of defining values of fundamental periods of vibration for our structure. We are going to use a precise, and I'm going to use the seismic analysis parameters. Okay, this depends on your position on the United States or in the world, I don't know. You have the site class and the different values depending on the spectrum and your location. Okay, I'm not going to dive deep on this. I'm just going to hit a site class of B, the S1 being 0.1, SS being 0.25, 2. The R will be 3. This also is different for each type of structure that you have. If you have a moment frame and or a concentric brace frame, this may be different. Okay, so now I'm just going to hit 3 over here and press OK. Also press OK over here. Very good, and this will generate these load cases for static seismic analysis. Okay, now let's go ahead and run the calculations. Okay, I'm going to press this button for the calculations. We found errors. We are going to take a look at them. I'm going to press yes. Now you have here a option which is, it is suggested to use the DSC algorithm in case of dynamic and nonlinear analysis of structure containing released directions. Containing releases, okay. The joists are released for bending at their end. This is an algorithm that facilitates dynamic and nonlinear analysis of structures with member end releases. It's just that. And you can read more about it in the help files, okay. So I'm just going to press yes. And we have an instability of type 3 detected at node 35. I'm also going to press yes. Yes once again. Okay, robot is running the model analysis. Now we have 2 warnings and 1 error. The warnings in blue and the error in red. The current joist span does not satisfy the minimum space requirements. You may choose a stiffer joist, but we are going to use the joist that we have. The DSC algorithm, it is a suggestion by Robot Structure Analysis. Not going to change that. And the instability type 3. Okay. You have mainly 3 types of instabilities in robot. You have type 1, type 2, and type 3. The instability type type 1 and 2, normally in this one you have in your stiffness matrix any element with stiffness 0. This is the case when you have a bar with 3 inches. Okay, and something like this is going to happen. The bar is going to this position to find a new point of equilibrium, and you may not use this. Okay, so when you have instability of type 1 and 2, something is really wrong in your structure and you should look at it. But if you have an instability of type 3, this means that you have you have some elements on your stiffness matrix that are much lower than the others. This is the case when you have elements that are much more stiffer than the others. Okay, if you model your structure this way or in a certain way, and you are certain of the way you are modeling, you may ignore these type 3 instabilities. Okay, if the results and the displacements have nice values, you may just ignore this, as I'm going to do right now, and then we will explore the results for bars, and if we find something odd, then we should take a look at this type 3 instability. Okay, by now I'm not going to do anything. Okay, sit and close. So thank you for watching. Please give this video a like, it will help me, and see you in the next video. Once again, thank you for watching.